Hi everyone, this webinar will be on surface processes which includes weathering, erosion and sedimentary rocks. So we're going to be looking at that rocks on the surface of the earth are continually changed by weathering. So weathering results in changes to not only the composition but the texture of rocks. So weathering can include processes where rocks break down into fragments or minerals in rocks react to form new, which are usually softer minerals. So weathering is due to the combination of either physical or chemical processes. So you should now be able to define the term weathering. So physical weathering is the physical breakdown of rocks into rock fragments without any change to the chemical composition of minerals. So there are many types of physical weathering. The first is salt crystallization or honeycomb weathering. This occurs only near the sea because it involves salt and affects both igneous and sedimentary rocks. So water enters the pores of the rocks and the salt crystals are left behind when the water evaporates. The salt crystals exert force when they crystallize on a small scale stress on the rock, which then enlarges the holes. We saw examples of honeycomb weathering when we went down to Second Valley, and this is how it forms. So frost wedging is another type of sedimentary weathering, and this is where water enters and fills the joints and cracks. The water then freezes overnight. We know as water freezes, it expands, and this causes stress on the rock surrounding it, and eventually it causes the cracks to become larger until pieces of rock start to fall off. Sandblasting occurs usually in desert regions where grains of sand are carried along by the wind. They brush up against the rock and they act like sandpaper. They grind away the rock and they take those little grains away with them. Lower parts of the rock tend to be more weathered than the top because that's where all the sand is concentrated. And you get these beautiful pedestal features that we can see here. Offloading is another type of physical weathering. So granite, as we know, is formed deep in the Earth's crust. When you remove rock material on top of granite, what it does is it releases pressure on the granite below. And what this stress does is causes the rock to fracture into what we call joints. So again, this is Granite Island, and you can see this jointing pattern along here. This is offloading as a result of weathering and erosion of the rock on top of the granite as it was starting to be uplifted and exposed on the surface. So exfoliation or onion skin weathering that we saw at Granite Island, at Granite Island, rocks tend to be poor conductors of heat. This means that the outer layers of granite will heat up during the day while the inside remains cool. Due to this expansion and contraction, what eventually happens is it causes stress between the inside and the outside of the layers of granite, and the outside layers will eventually peel off into this onion weathering here. So, chemical weathering involves the reaction between minerals present in rocks and substances present in the atmosphere and groundwater. So these reactions cause new minerals to form, and the agents of erosion easily carry these newly formed minerals away. So chemical weathering occurs because the most rock-forming minerals are formed under conditions of high temperature and pressure, either by solidification of magma or during metamorphic change. They are therefore unstable under the low temperatures and pressure conditions of the Earth's surface and react readily with water, oxygen, or carbon dioxide. So solution is a type of chemical weathering where rainwater can dissolve substances, for example, carbon dioxide, and it can become corrosive and react with the minerals in the rocks. So carbonic acid is acid rain, and it's formed when rainwater dissolves carbon dioxide, and this acts as a weak acid that reacts very effectively with limestone, and what it does is it forms a soluble calcium bicarbonate. This calcium bicarbonate solution then is moved away, eventually cools and solidifies and precipitates into stalagmites or stalactites. So this is the formation that creates limestone caves like we see along the southeast coast in Naracoorte Caves, for example, which is also where I'm going to be on my field trip or my holiday that I'm going on over the weekend. And I will get to see some beautiful stalagmites and stalactites in Naracoorte Caves. So hydration is another type of chemical weathering. So minerals can absorb water, which causes them to expand. And these large crystals will exert pressure on the surrounding crystals, and this results in disintegration of the rock. So hematite, for example, absorbs water and then forms limonite. Oxidation is another type of chemical weathering. This is where certain minerals will react with oxygen to form oxides or oxygen and water to form hydroxides. So minerals containing iron tend to be very susceptible to oxygen. So oxidation of iron minerals results in the red and yellow color of many rocks and soils. So hornblende or augite, for example, when reacting with oxygen will form hematite or limonite. And this is why the soil in the middle of Australia is red. It's because it has iron in it and has oxidized as well as being physically weathered into smaller particles. Another type of chemical weathering is spheroidal weathering, and this is where it affects the outside of the rocks. Water penetrates the joints in the rocks, and then chemical weathering occurs on the outer layers of the rock, making the block weaken and the corners to become rounded, like we can see here. So only the corners are chemically weathered to create spheroidal weathering. Now, the products of weathering are rock fragments, for example, quartz, and that's physical weathering. Or it can be new minerals like clay minerals, which are the products of chemical weathering. Okay, so you should now be able to explain the principles of physical and chemical weathering and explain how weathering processes change rocks on the surface of the Earth. Okay, we're now going to be looking at erosion. So erosion is the removal of products of weathering from where they were formed. These materials can be transported over long distances or short distances, and the types of erosion can be gravity, water, ice, or wind. You should now be able to explain the difference between weathering and erosion. And the products, so we're now looking at the products of weathering are eroded by wind, water, ice, and gravity, and are eventually deposited. So looking at gravity erosion, this is where you get loosened rock fragments that tumble down a slope. Mass wasting is the rapid downhill movement of fragments, and usually the fragments don't actually move that far away from one another, but they move all together into one pile. So this form of erosion usually occurs in very dry or cold climates and usually forms scree slopes. So for example, we've got a mass wasting event here, which is also known as a landslide, and we've got another mass wasting event here on the cliffs of Dover, or the White Cliffs of Dover. Okay, so water is a very significant agent of erosion, and it can transport materials by 5 processes. It can transport it through solution, which is where dissolved salts are carried through a solution in the water. It can transport via suspension, which is where the energy of the water carries fine particles in suspension. And it's usually concentrated more towards the base of the river. Saltation is where small pebbles will bounce along the bottom, where you can see here, this pebble bouncing along and that pebble bouncing along. Rolling is where pebbles will roll along the bed of the river or form of water. And sliding is where large rocks slide along the bottom here. Now, wind will also transport smaller rock fragments, not as large as water can, but they do it by the same 4 of 5 processes also used by water. So they can roll, slide, saltation, or suspension. So this is a picture of a sandstorm just off the Gobi Desert, and this would be rolling, sliding, and suspension of wind erosion. Okay, so ice can be a very effective erosion device, and glaciers are usually the mechanism that allows for erosion of material. So glaciers are rivers of ice that flow from high ground to low ground, and though they don't really move at a very fast pace, they do move usually around several meters during the year. And what they do is they tear rock fragments from the sides of valleys and transport that rock down into the valley. So this is a glacial valley. It has a very distinct U shape, and the ice, the glacier, has literally carved this U. And what you'll see is you'll find a lot of boulders in the valley that have been eroded from up here and transported down here. So till and tillite are products of erosion through ice. So rock debris that's been transported by a glacier is known as a moraine. So this down here is a glacial moraine. And when it melts, it deposits unsorted angular debris, which is your till. Okay? The till can then be consolidated and lithified to form a sedimentary rock called a tillite, which we'll be looking at later in this set of slides. Glaciers can also leave erratics behind as well. Erratics are usually large boulders that have been carried over distances, and they're left when the glacier retreats and the boulders are left behind. So this is an erratic from Yellowstone National Park, when there used to be a glacier that has obviously retreated and left this massive erratic behind. So glacial pavement is the last, I guess, formation that is left by erosion through ice. And this is where, when glaciers move down valleys, they drag large quantities of rock debris. Some of this rock debris is known as rock flour, which is really fine-grained material. And what that does is that it polishes the bedrock on which the glacier is moving and creates a really smooth surface. You also get coarser pieces of rock that are stuck in the bottom of the glacier that grind and scratch the surface, that leave striations and chatter marks. And you'll see this at Hallett Cove when we go next term. So you should now be able to describe and explain the actions of wind, water, ice, and gravity as agents that transport the products of rock weathering. So sorting, as we know, can help define a sedimentary rock. And when you have erosion of material, sorting does matter as well. So rock debris can be transported and deposited by gravity, wind, water, and ice. But it's also sorted either to a greater or lesser extent, and depending on the size of the grains involved. So sedimentary rocks are either described as poorly sorted, so you've got a large variety of grain sizes, moderately sorted, so the grain sizes are more similar in size, or well sorted, where all of the grains are usually roughly the same size. So gravity and ice don't sort rock fragments very well. So the debris transported by these agents consist of fragments which have a wide range of sources or sizes, and therefore are considered to be poorly sorted. Water tends to be a moderate sorter of material, meaning that fine material is carried out further, but large pebbles and boulders are usually kept. So water is more of a moderate sorting. Coarse material, so sand dunes, which usually consist essentially of wind-blown transported material and tend to be very well sorted and consist entirely of sand-sized grain sizes. So this is wind transport, this is water, and this is gravity and ice. Okay, so sedimentary grains can also be described as being either angular, subangular, subrounded, or rounded. Grains that have been transported a long distance are likely to be rounded. So angular grains indicate that either minimal transportation has occurred or transportation by gravity or ice has occurred. So you should now be able to compare the sorting and rounding effects of these transporting agents. So the energy of an environment also impacts on how materials are transported. So a high energy environment means you've got a fast moving, turbulent erosion source as either air or water. And the higher the energy, the larger the fragments that can be transported. A low energy environment is usually air that or water that's moving slowly, if at all, and it only transports fine grained material like mud, silt, or clay. As the energy of the transport medium decreases, the heaviest material is deposited first. So a medium energy river entering the sea provides a very good example of gradual deposition of sediments with respect to their size. So the gravel will be dumped first, then the sand and the clay and the silt will finally settle on top. A river that's traveling from a mountainous region to a flat area provides an example of a sudden sediment deposition, and this material is deposited at the base of the mountains forms a feature called an alluvial fan. You get the coarser grain material here and the finer grain material out here. It's not usually, or can be, but not always, will be in a water environment. So this one isn't in a water environment. So you should now be able to explain the relationship of the energy of an environment to the type of material transported and deposited. So sedimentary rocks are formed from products of weathering and erosion. Formation of sedimentary rocks occur over a long period of time. They occur through the products of weathering and erosion and may become consolidated to form a sedimentary rock. The important processes when forming a sedimentary rock include compaction and sedimentation, which together is known as lithification. So grains are compacted by the pressure of the overlying sediments, so in here, and then they're cemented together either as usually as salts that are dissolved in groundwater that are present in the pores, and that glues the rock together. So you should now be able to explain how sediments are changed into sedimentary rocks by compaction and cementation over time. Now we are going to be looking at common sedimentary rocks. So the texture of a sedimentary rock is described in terms of grain size, grain shape, and sorting. Now, clasts are the pieces of weathered rock material that make up a sedimentary rock, and these are usually glued together by a cement. Now, there are three common cements that are used: calcium carbonate, iron oxides, or silica. So if you've got a sandstone that was glued together by calcium carbonate, it'll fizz. If you've got a sandstone that was glued together by iron oxides, it'll likely be red in color. And if it's glued together by silica, it'll be really hard because silica is quartz, which has a hardness of 7. So the first common sedimentary rock is a conglomerate. This is a poorly sorted rock. It has rounded pebble-sized clast that is suspended in a fine grained matrix, and it's usually formed at beaches or on floodplains. Sandstone is the next one. It has a grain size of 1 millimeter and consists of quartz cemented together. It's deposited in either marine environments, aeolian environments such as sand dunes, or a fluvial environment such as a river. They tend to be well sorted and well rounded, and not all sandstones are the same color. Shale is a fine-grained and well-sorted sedimentary rock. It's made of clay minerals with some quartz. It tends to be smooth and is relatively soft because clay is a soft mineral. It's produced or it's a product of chemical weathering of feldspars and mica into clay, and it's transported long distances from the shore of a lake or sea, and it tends to be deposited in a low-energy environment, such as deep sea marine. Tillite is consolidated material left behind when a glacier retreats and melts, and consists of unsorted and angular fragments of different rock types. Fossiliferous limestone is formed by the cementation of remnants of marine organisms. So organisms in the limestone tend to indicate where it was formed. If it has coral in the limestone, then it's a warm, shallow sea environment. If you've got, say here, crushed shell fragments, this means shallow marine in a high energy because the fragments are crushed. Calcrete is the last type of sedimentary rock that we're going to look at, which is formed below the surface of the soil in regions of dry climates. And it forms when there isn't enough rain to wash away soluble salts and that are produced by chemical weathering.